Right. Good morning, everyone. So we are recording now. So far, we have covered weak duality and strong duality, right? We also proved strong duality for standard equality form LPs yesterday, using the fact that simplex terminates, simplex with Bland's rule terminates, right? Good. And we looked at one example, and I mentioned that today we're going to look at another important aspect of duality, which is called complementary slackness. Okay, so that's what I want to cover today. And as I mentioned, it's going to be very useful when we design primal dual algorithms in module 5. In fact, it's going to be one of the main things we will rely on for the intuition behind our algorithms and also for the correctness. Okay. All right. Are there any questions or concerns pertaining to weak duality, strong duality so far? One way to check whether you've really understood weak duality and strong duality and the difference between them is to go to this table that we created and try to fill it in yourself. Okay, if you are unable to fill it in yourself, that means that you are lacking understanding of duality. All right. Okay, so let's look at a primal dual pair of LPs. So here is the example. So the primal is maximize 4, 1, 5, 3 x subject to 1, minus 1, minus 1, 3, 5, 1, 3, 8, minus 1, 2, 3, minus 5 x, and I'm going to use a different form. This is not standard equality form. Right, so we have the form ax less than equal to b and x is non-negative. All right, and let's write down the dual quickly. So the primal is a maximization problem, the dual is going to be minimization, and we are going to have b transpose y for the dual variables y subject to, let's take the transpose of this matrix. So we have 1, minus 1, minus 1, 3, 5, 1, 3, 8, and minus 1, 2, 3, minus 5. Right, minimize B transpose Y subject to A transpose Y question mark C, and what are the Y's? Can somebody tell me what do I need to put in these question marks? Oh, maybe I should write down the C. The C is 4153. So can someone fill in these question marks for me using our discussion on natural and unnatural?
This should be greater than or equal to.
Both of them, right?
First, both of them should be greater than.
Okay. Right? Because notice that on the left hand side, both of them are natural. The constraints are also natural and the variables are non-negative, which means natural. And so on the right hand side, in the dual, you will also have everything natural, right? Okay. All right, so that's correct. All right, so I want to give you some do-it-yourself problems related to these LPs, just for practice. It's stuff that we have already studied in this course. So the first one is very easy. Transform the given LP P to SCF LP P prime. Okay, that should be very easy. And the second point is, once you have the SCF LP, I want you to solve the SCF LP using simplex. And all right, so those are the problems. And what you will find using simplex, just so that you can check your work, and I want to use it right now in our example. So the last dictionary will be 2, 4, and 6 in P prime. Notice that P prime will have more variables than P. In fact, some of you might already be able to see how to transform. It's a very easy transformation. So the basis will be 2, 4, 6, and the corresponding optimal solution of P prime will be 0, 14, 0, 5, 0, 1, 0. Let me just make some space here. So it's going to be 0, 14, 0, 5, 0, 1, 0. And the corresponding optimal solution for the original LP will simply be the first 4 entries. Okay, you can check this using the transformation you did. All right. And the third point I want you to do is I also want you to find the certificate of optimality. And I will tell you what it is so that you can check your work. So the certificate of optimality you will get for the dual, right? So it will be, which will basically be an optimal solution for the dual, right? So this is nothing but optimal solution for the dual LP. And this one you will find as 1106. Okay, so I just want to use these two vectors right now, x bar and y bar. And I want to try to see what's going on in these two vectors. All right, so these are just some things you should try on your own. And I've given you the answers so that you can verify your work. So let's consider x bar 0, 14, 0, 5 and y bar, which is 1106. Okay. All right, I want to do one more thing. I want to number the constraints and I want to put down the variables in the other LP corresponding to those constraints. Okay, so I'll do this in red color. So this is our first constraint of the primal, second constraint, and third constraint. And the corresponding variables are y1, y2, and y3. I should have had more space here, but it's okay. I'll squeeze it in. 1, 2, 3, and 4 constraints. And the corresponding dual variables, the corresponding primal variables, which will be the dual of the dual, are x1, x2, x3, and x4. Okay. So let us look at the tight constraints for x bar with respect to the LPP, right? X bar is a feasible solution for P. So when I say tight of x bar, I'm referring to which constraints are tight for the solution x bar with respect to the linear program P. Okay. So what are these constraints? Can someone tell me? If you plug in 0, 14, 0, 5 into ax less than equal to b, what are the constraints that are satisfied tightly? There are three constraints, 1, 2, and 3. I know it's 9 in the morning, but it's just arithmetic.
One and three.
1 and 3, right? So notice that constraints 1 and 3 are tight for x bar. All right. Okay. Can somebody tell me what are the tight constraints for y bar with respect to the corresponding LP? So the dual LP. So if you plug in 1106 into A transpose Y at least B transpose, A transpose Y at least C, which ones are tight?
2 and 4. Sir.
2 and 4. Okay, yes, that's right. Okay, all right. Observe that the constraints that are not tight for x bar, so in particular, constraint 2 is not tight for x bar, and the corresponding dual variable, so I'm looking at constraint 2, right? So the corresponding dual variable is y2. And if you look at y bar 2, you see a 0. Okay? And the corresponding dual variable, so I'll write it here accordingly here. So okay, in fact, it is the only 0 entry in this dual solution, y bar. Okay? Observe that the constraints that are not tight for y bar, they are 1 and 3. Constraints 1 and 3 are not tight for y bar. And what do you see about the corresponding primal variables? So can someone tell me what are the corresponding primal variables?
Zero. X1, X3.
X1 bar and X3 bar, and they are both 0. And the corresponding primal variables X1 bar is 0 and X3 bar is also 0. Okay. So the constraints that are not tight, in all those cases, the corresponding variable in the other LP is 0. Right? In other words, so I also want to introduce some notation. Let's see. In particular, for the three constraints of the primal either the ith constraint is of the primal is tight for x bar, or the dual variable yi bar is equal to 0. And likewise, for all of the 4 constraints of the dual, either the jth constraint of the dual is tight for y bar, or the corresponding primal variable xj bar is equal to 0. Right? Just some observations. Okay, so all of this is simply observations for the given feasible solution. I just want to introduce some notation to make things a bit easier. So the one way to think about the ith constraint being tight is to think of it as, so if this is your matrix A as usual, and this is your B, and this is your C, right? So what we are saying is that if you looked at the row I of the matrix A and you multiply it with x bar, you will get exactly the right hand side, which is BI. Okay, so that's just a notation that we will find useful. Okay, so the constraint being tight is the same as writing down this equation. And similarly, for the sake of completeness here, what we are doing is we are multiplying the row J of A transpose into Y bar, and we are getting the Cj on the right hand side. It's an equality. Okay. So for every single constraint, either the constraint is tight or the corresponding variable in the dual LP, right? I can just say dual because the dual of the dual is primal. So the corresponding variable in the dual, if the constraint is not tight, then it has to be 0. That's the observation. And the question is this a coincidence?
Sir, hello.
Yeah, go ahead.
So, sir, if, for example, in a first observation, sir, if yi bar will not be equals to 0, in that case, sir, can we say that ith constraint will be tight for x bar?
Right, exactly. So one of these two will always hold, and that is the theorem we are going to prove. So if the dual variable, if the variable is not 0, then the constraint has to be tight.
Okay, sir.
Right, so that's exactly what we are going to prove, that whenever you have optimal solutions for both the primal and dual, they must satisfy these conditions that we have written down here. I'll write them more generally, but for this example, it's this way, right? So these conditions are basically called complementary slackness conditions. So the answer is, it is not a coincidence. And this is exactly the complementary slackness theorem that we are going to prove. All right, so let's write down the theorem. So this is, it's similar to theorem 4.6. Sorry, it's similar to theorem 4.5 in the text. I have made a slight change by looking at a different type of form of LP. All right, so your primal is maximize C transpose X subject to AX less than equal to B and X is non-negative. and the dual, as we wrote down, B transpose Y, subject to A transpose Y, at least C, and Y is non-negative. Okay, so that's just the general form of the specific example we considered. Okay, so consider the primal dual pair and let A be an M by N matrix. All right, so let's suppose you are given a feasible solution to the primal and Y bar is a feasible solution to the dual. So the theorem says that both of these are optimal solutions. X bar and Y bar are optimal for the primal and the dual respectively, if and only if the complementary slackness conditions hold. So I'll just write them down in full once again. Right. So for all I in 1 up to M, either the ith constraint is tight of the primal or the dual variable yi bar is 0. And I want to emphasize that both of these can also happen, right? Of course, OR generally means, it does not mean XOR, generally speaking, right? I just want to make it clear that both these conditions could hold. That's okay. And similarly, for all the constraints of the dual, either the jth constraint is tight for the dual solution, or the primal variable x j bar is equal to 0. Okay. This is what we will prove. So these conditions, as I mentioned earlier, they are called the complementary slackness conditions. And we will be using them heavily in module 5 for designing primal dual algorithms. In fact, the very intuition of most of our algorithms will be based on finding solutions that satisfy the complementary slackness conditions. And because they satisfy the complementary slackness conditions, it will follow that we have found optimal solutions. Of course, there we are dealing with combinatorial optimization problems. So we will first have to check how to solve them using linear programming. So all of that will be tied together. Okay. And these conditions, if they don't remind you, it's probably a good idea to go to assignment 1 again after the lecture. So they should remind you of assignment 1, problem 5. That is one of the reasons I put the problem there in the first place. Okay. So in assignment 1, problem 5, you proved something using counting arguments. Turns out, if you knew the theory of duality, you could have also just applied it there and proved it using that. All right. All right, are there any questions or concerns about the statement of this theorem? Okay, so if there are no questions, let's, so what we will do is we will prove this theorem. I just want to make a quick remark. So I say it is similar to theorem 4.5. So in there, they consider a different form of LP. They consider maximize C transpose X subject to AX less than equal to B and X is a free variable. Okay, so that is the form they consider in the text. I'm going to do it for this form because this form is actually more elaborate. It actually will have more complementary slackness conditions. Why? Because notice that if you have a free variable, then the corresponding constraints are always equality. So saying that the constraint holds tightly or the variable is 0 is actually trivial because the constraint is already an equality constraint, right? So complementary slackness conditions, they make sense only when you have inequality constraints. If you have equality constraints, then they are trivially true. They will always hold. Okay, so that's why I'm considering a form where everything is an inequality. There are no equations and there are no free variables. Okay, the theorem holds for all linear programs and their duals. I will do an example at the end today or otherwise on Monday for a linear program that is in an arbitrary form, right? So some of them will be less than equal to, greater than equal to, and so on, right? But the complementary slackness theorem holds there as well. But we will prove it only for this case. As I said, there are no new mathematical ideas when you go to the general case. It's just a matter of bookkeeping and keeping the different constraints, sort of dealing with them separately. Okay, so it doesn't really bring any new mathematical ideas. All right. So if there are no questions, let's proceed to prove this theorem. Right. All right, so let's see what we are given. We are given, so we have to prove two directions. I'm going to focus on the forward direction. Most of the things are reversible, so I want you to be able to do the reverse direction. Okay, but whenever things are reversible, I'll probably just write down if and only if statements. And this is something you might have also noticed in assignment 1 problem 5. The two directions part B were actually, yeah, this is actually part B. They were actually very similar. Okay, so let's say we are given X bar and Y bar. They are feasible solutions, but let's assume that they are optimal solutions. Okay, so we are moving the forward direction. So, what can you tell by strong duality?
C transpose X is equal to C transpose Y.
C transpose X bar is equal to B transpose Y bar. Okay, so we're going to make use of this. All right. Okay, so let's just put this in brackets here. We'll come to it when we need it. All right. So since X bar is a feasible solution for the primal, we know that A X bar is less than equal to B, right? That's our LP, AX less than equal to B, X non-negative. Okay, let's write down on the right side, since y bar is feasible for the dual, we know that A transpose y bar is at least C. Okay. I want to write down this differently. Let's see. So instead of A transpose, I want to have A, right? So I'm going to take the transpose on both sides. And what that gives me is y bar transpose A is at least C transpose. Okay. Now, since y bar is a non-negative vector, notice that in our primal and dual, both x and y are non-negative. So since y bar is non-negative, I could very well multiply both sides here by y bar transpose. Okay, and I could do the same thing here. Since x bar is non-negative, I can multiply both sides by x bar. So I get y bar transpose A x bar is at least C transpose x bar. Okay, let's combine the information we have so far. Okay, so we've got these two inequalities, and you see that there is a common term there, right? So in particular, C transpose x bar is less than equal to y bar transpose Ax bar, which in turn is less than equal to y bar transpose B. And notice that y bar transpose B is the same as B transpose y bar. So what can you conclude now? Can someone tell me what's the next thing to consider?
The SD condition, sir.
Right, but what should how should I get there? What should my next conclusion be? You look at this inequality. At this point, what do you conclude? Using an observation we made earlier.
We should have equality completely.
Exactly. Because of strong duality, we know that everything holds with equality. Right? So, in particular, C transpose x bar is equal to y bar transpose Ax bar is equal to y bar transpose B. Okay. In particular, what we are saying is that equality holds everywhere, because otherwise you would not have an equality between the left and the right. All right, so from here, we want to get to the complementary slackness conditions, right? So we have two things here. Here is the first equation, and here is the second equation. And we want two conditions, CS1 and CS2. So each of these equations is going to give us one of the conditions. All right, I'll do one of them for you, and you can do the other one by simply imitating that. Okay, so we have two equations. Each one will give us one of the CS conditions. All right, so let's look at the second one. let's consider y bar transpose ax bar is equal to y bar transpose b. Okay, and on the right side, I'll say consider C transpose x bar is equal to y bar transpose ax bar. And here I'm going to say, do it yourself. Let's do the first one, okay? Or rather, the second equation. All right, so what does this mean? This means that y bar transpose ax bar minus y bar transpose b is equal to 0. This means that y bar transpose times ax bar minus b is equal to 0. Now, can someone tell me how to proceed? How should we get to one of the CS conditions? And in fact, can you tell me which CS condition we are going to derive from this equation? So look at this equation, y bar transpose times ax bar minus b equal to 0. Which CS condition will this take us to? Is it the first one or is it the second?
First one, sir.
First one, exactly. So what we want to do is we want to, from here, we want to get to the fact that the first CS condition holds. Right? And what is the first CS condition? Let's just write it down. It says that either the ith constraint of the primal is tight or the dual variable is 0. For all I, either ith constraint of the primal is tight for x bar or the corresponding dual variable yi bar is equal to 0. Okay, so we still need to figure out how to get there. Can someone help out?
Ax bar minus b is less than or equal to 0. So
Okay.
if the row is strictly less than 0 and the
Okay.
corresponding yi is not 0, then that would give a negative term and it won't be equal to 0.
Okay, I see that you can probably see how this all works out. Can you give me a form in summation? Can we write down everything as a summation?
Yes, sir.
Okay,
Summation of
how would
the
that proceed?
summation of y bar I
Okay,
into the specific row constraint.
right,
I mean
right.
corresponding.
And I goes from 1 to m, right? So notice that we are multiplying a row vector, just to make it clear to everybody else, we are multiplying a row vector by a column vector, right? That just means that we are multiplying them entry by entry and adding up the numbers, right? So what you really have here is a summation I going from 1 to m, multiply each entry of y bar, so that would be y bar I multiplied by the corresponding column entry for ax bar minus b, right? And what would that mean? It would mean that you take the ith row of the matrix A multiplied by x bar and subtract b I bar. Does everybody agree with this conclusion? Sorry, I don't know why I put a bar here. My bad. There are no bi bars. There are only bi's. Okay, right. So we are taking the ith row of A matrix, multiplying it by x bar, and subtracting bi from it. Does everybody agree that this is exactly the previous line, and we want this to be equal to 0? Right? So we're adding a bunch of numbers and getting 0 out of it. Right? So that means that for each of these, and notice that y transpose ax is always less than equal to y transpose b. So you're basically adding a bunch of, right. So the only way this can happen is if for every single entry, either the yi bar is 0 or the corresponding other part, rho I times rho I a x bar minus bi is equal to 0. And that is exactly what we want to prove. Right. So in particular, this implies that for all I going from 1 to m, either yi bar is 0 or right. And this is exactly what we are saying. So this is the same as saying this is equal to b. Right. So either the ith constraint holds tightly for x bar in the primal, or the corresponding dual variable is 0. Okay. Are there any questions at this point? Maybe I should point out that notice that these are non-negative and that all of these are also non-negative, right? Because ax is less than equal to b, so ax minus b, is that correct? Did I make a mistake here or is this correct? So I'm a bit confused. The condition says ax less than equal to b, so ax minus b is less than equal to 0. But that's not what I'm writing here. Ax minus b is greater than equal to 0. So do I need to multiply both sides by negative?
So even if that was the case, the analysis won't change, no, sir? Like it should be less than or equal to 0, but the analysis won't change, no, sir?
Is that true?
Yes, sir. So even if it is less than, the same procedure can hold for it. So
Okay.
he'll just say if
Like if the constraint is not tight, it will be either negative or positive. Like it should be negative. It was less than or equal to 0. And
Yeah.
if y is not 0, then multiplying that with the constraint will give you a strictly negative number.
Ah, that's right. Okay. Good. Sorry. Yes. These are all at least 0. These are all at most 0. Right. Okay. Good. So we are adding a bunch of right. So you're multiplying a non-negative number by a non-positive number, right? And that will always give you something non-positive. You all agree? So we're adding a bunch of non-positive numbers and getting 0. And the only way that is possible is if all of the numbers are 0. If any of them was strictly non-positive, I mean negative, then the sum would also be negative. Right? So it's fine, right? So notice that the product of these two, the product will always be less than equal to 0, because one of them is non-negative, one of them is non-positive. So if you're adding a bunch of less than equal to 0 numbers and you're getting 0 as your answer, the only way it's possible is for all of them to be 0. I guess I'm just so used to non-negative that I got thoroughly confused over there. Okay. Are there any questions or concerns at this point? I guess the human brain is really not wired to deal with negative numbers. All right, let me just make this clearer here. So I wrote ax bar equals b. Okay. So the first condition holds, and we got that by considering the second equation. And I want you all to start with the first equation and get to the second condition, right? So you want to get a bunch of statements and show that the complementary slackness condition 2 also holds. Okay, so this is the forward direction, and you can see that most of the things we did are if and only if. So I want you all to think about why the converse direction also goes through, right? So maybe I'll just say the converse direction, do it yourself. I want to point out one subtlety. In the forward direction, we are using strong duality. In the converse direction, if I am understanding correctly, and if I did the things in my head correctly, you actually don't use the strong duality. You immediately start from the CS conditions and you work your way backwards, and you will arrive at this equation. And that implies that C transpose X bar is equal to Y bar transpose B. And by weak duality, X bar and Y bar are optimal. So in the forward direction, you're using strong duality, and in the reverse direction, you will be using weak duality. Okay. All right. So that's the complementary slackness theorem. I want to write down the general form, and then that will be, we'll conclude the lecture over there. Right. So let's see. Okay, so I'll just write down the general form. So P and D is any primal dual pair, arbitrary. By arbitrary, I mean it's not in any special form. It's just any primal dual pair of LPs. And let's say X bar is feasible for the primal, and Y bar is feasible for the dual. Then X bar is optimal for the primal, and Y bar is optimal for the dual if and only if X bar and Y bar satisfy the complementary slackness conditions. And we will do an example next time of arbitrary LPs and write down all the conditions, right? So the conditions in general always say that either the constraint in the primal is tight for x bar, or the corresponding dual variable is 0. And similarly, in the other way, either the dual constraint is tight or the corresponding primal variable is 0. Okay, so on Monday, we will do a concrete example of an arbitrary LP and its primal CS conditions. We'll just write down the CS conditions. And then I want to go back to geometry and think about optimality from the geometric point of view. And we will also see how the CS conditions and some other notions can be viewed through the lens of geometry. Okay, so we started with geometry when we started LPs, and we are going to end with geometry. And then we are going to the next module where we will use duality to get our combinatorial optimization algorithms, to understand why they work, and to prove their correctness, etc. Okay, that's all for today. I'm here for another 10 minutes in case there are any questions or concerns.